Good afternoon, all. In the post-lunch session, today I'm very happy. We are very happy to get Professor Anjan Barman from in SNBNCBS National Center of Basic Science. As I told you before, he is one of the pioneer in the magnetism. And Professor, to brief about Professor Anjan Barman, Professor Anjan Barman obtained his PhD from the Indian Association for the Cultivation of Science under Jadavpur University, Kolkata in 1999. He worked as a postdoctoral fellow in Technical Israel University of AICTE and University of Leeds, UK, and University of California, USA. Subsequently, he worked as an assistant professor in the University of South Carolina, Columbia at USA, and Indian Institute of Technology, IIT Delhi, between 26 and 29 before joining the SNBNCBS National Center for Basic Sciences, Kolkata, India in 29, where he is a senior professor now. Professor Barman leads the spintonic and spin dynamic research group here with world-class laboratories with indigenously built experimental setups. He has guided several and graduated several PhD students, more than 25 PhD students, and more than 50 masters and bachelor students during his tenure. He has published more than 200 research papers in international journals and books, and a monograph titled Spin Dynamics and Damping in Ferromagnetic Thin Films and Nanostructures from Springer. He serves as a editorial board member of the journals Nanotechnology of IOP, Scientific Reports in Nature Group journals, and Pravanna. He also reviews research grant proposals from various countries in the world. He is a recipient of Material Research Society of India Medal and elected fellow of Indian Academy of Sciences, Bangalore. With this short biography, I'd like to request Professor Anjan Barman to take the session charge. Thank you, sir. Please, sir.
Thank you very much for a very kind introduction. Yeah, so let me start. So, as I said, this is a sort of a lecture divided into two parts. So today I'll try to finish. I don't know how much I can finish today. Magnetization dynamics from theory to experiment, because this is a very new topic to many of you. So before starting the actually the the various techniques and some showing you some results, I will introduce to you various basic theories also, and that's why I named it as from theory to experiment. And even before that, I'll just briefly show you the research activities in our group. I set up my group in SNBNCBS Center in 2009, and before that in IIT Delhi I was for 3 years. So we work primarily on various topics like femtosecond demagnetization, and then we work on a new field called magnonics, which is an artificial crystal where spin waves are used to carry information, and I'll show some part of it in my talk. I also work on various interface effects in magnetic heterostructures, and then I use something called spin orbit effect to sort of influence the spintronics or spin transport, which is also called spin orbit torque, and spin Hall effect. You probably heard about ordinary Hall effect and anomalous Hall effect, and I will introduce to you what is spin Hall effect. Then another interaction called interfacial Zyloshinsky-Moria interaction, and something called magnetic fermions, which is a very hot topic now. So you don't have to understand anything right now. I'm just giving you names of this. Magnetic vortex, which is also a very topological soliton, which is interesting property. And then various material, 2D material spintronics, Heuser alloy thin films, and so on. And we used several indigenously built techniques, which are unique in India and very rarely found in various international labs. And one of these is the time-resolved magneto-optical car microscope. And you also use a femtosecond optical pump spectroscopy. We have developed in our lab a broadband ferromagnetic resonance and spin torque ferromagnetic resonance. We also have developed something called a conventional Brillouin spectroscopy. You may have heard about Raman spectroscopy. Brillouin spectroscopy is quite different than that, although the principle is same. And micro-focused Brillouin spectroscopy. And in addition to that, I use several standard techniques like static Moog, vibrating sample magnetometer, and magnetic force microscope, which are standard. I mean, this is the only standard thing that you use, and all of these are non-standard and indigenously built in our lab. And some of the glimpses of the labs that I will, this is the time-resolved Moog microscope, These are all optical techniques. This is electrical technique, FMR. This is femtosecond amplifier lab. And this is called the Brillo light scattering lab, micro Brillo light scattering. We also have a terahertz time domain spectroscopy lab. And these are some of the fabrication and characterization techniques. During my tenure, I also have worked to develop various nanofabrication and characterization facilities. And we have a class 100 and class 1000 clean room. And that includes something called ICP-RIE, electron beam evaporator, and of course, photolithography, dual beam FIB and EBL, electron beam lithography, various wet chemical room. We also have maskless pattern generator and other things right now. So it's a very, handy and very, sort of, I would say, high quality lab. And outline of my talk will be challenges and applications in nanomagnetism. I'll give some theoretical backgrounds. And today I will talk about primarily various techniques like high frequency measurement techniques and probably a little bit of fabrication if I have time. Time resolved magneto-optical Carr effect, Brillo light scattering, broadband ferromagnetic resonance, spin torque ferromagnetic resonance, and so on. So you'll learn what are the principles of those and how they work. So challenges of nanomagnetism. You can see on the left side, you have a magnetic compass. And as you know, that was invented in sort of 2nd century BC, between 2nd century BC and 1st century AD in China. And they were used to use it for fortune telling. And later on, it started to use for navigating. So that was the first device, you can say magnetic device. And then slowly with modernization of civilization, we have many, many magnetic devices. One of them very important is the induction motor and the magnetic tracker. And more recently, you have magnetic hard disk, RAM, and so on. So the grand challenges in magnetism are, like you can see, start from ultra strong permanent magnets. You use it in various parts of, sort of electronic, mechanical, and various kinds of, devices. And then ultra high density media. So you want to store more and more data into very small area. So you need to go for ultra high density media, spin transistor with gain. That would be fantastic. 100% spin polarized materials. So for growing many of those, you need very high quality material with nearly 100% spin polarization. You need room temperature magnetic semiconductor, where you have both magnetic and semiconducting property. Then instant boot up computer. So right now, if you switch on your computer, it takes some time to boot up because you have, some part of it, which actually the processors and other things, RAMs, it takes some time, charge-based RAM, it takes some time. Whereas if you have magnetic RAM and, other magnetic processor, then they can, store the information. Charge-based information are lost when you switch off the power, but the spin-based information are retained because, in a ferromagnet, you can retain the magnetization even when you take, withdraw the magnetic field. So that can give rise to instant boot up computer, then magnetic logic, spin-based qubits, and so on. So computer from test tube and so on. So you can have nanobiomagnetic sensors. I mean, there are, you name it, there are many, many interesting applications. And that is why these are the grand challenges. And many of them are being met. Actually, most of them are being met very, and being researched very, rigorously and vigorously, I would say. So because my talk is primarily on magnetization dynamics with applications in computer computational devices. So I would start by trying to motivate you by saying, is all spin-based computer possible? And you can see there is the architecture of von Neumann computer. And you can see the input-output devices, external storage, memory, all of them have been made magnetic. We already have magnetic, read-write devices. Magnetic RAM is already there. It is actually trying to compete with the charge-based and other kind of RAM. You can also have magnetic oscillators. We can supply gigahertz frequency power. The only thing missing so far is the processor. And for developing a all magnetic processor or in other words, all magnetic computer, you need to have these kind of things, the spin logic, spin wave communications, signal processing, and everything. So if you can do that, and this is a far-fetched idea, then the whole computer can be made on a single chip and made of only magnetic material. It will be extremely fast, energy efficient, and will be very, very cost effective because you can grow everything in a single chamber on a single go. So you probably have, some of you have probably heard that magnetic recording is already there. And in 2007, Albert Farth and Peter Grunberg actually won Nobel Prize in Physics for discovering this giant magnetoresistance, the work they had done in 1987-88. So what is that, and then how it actually works? So here you have a magnetic recording media with magnetic bits. So you can see these yellow arrows, they actually show the direction of magnetization within these small bits. So they are written in certain amount of magnetic rings, and they are written by a miniaturized electromagnet. So the field from the electromagnet, it creates a localized field, and it can write that small part or bit of the media. And once it is written, they actually are stored like that. And then depending on their direction, so whether they are head to head or tail to tail or head to tail, the stray magnetic field from them will be different. Okay. And that stray magnetic field can be now read by this sensor, which is called the giant magnetoresistive sensor. How does it work? It has two layers. One is a fixed magnetic layer, whose magnetization is fixed by another antiferromagnetic layer. So this is called a pinned layer. And then you have a free magnetic layer, which is made of, say, permalloy or NIFE, an alloy. So its magnetization can rotate, freely. And then you have a, spacer layer, which is in this case is copper. So this is called a GMR or spin valve sensor. If you now take it to this, magnetic media, the stray magnetic field from this will now rotate, or sort of magnetization of this, align the magnetization of this layer, either parallel to this layer or anti-parallel to this layer. So when they are parallel, if you now start sending current and measure the resistance will be either, when they're parallel, will be very small, and when they're anti-parallel will be very large. So you'll have a two resistive state or a binary resistance state, and that depends on the direction of the bits. So just by reading the resistance, you can actually read the configuration of the bits. So that's how the magnetic read-write device works. And of course, it is facing many bottlenecks. Further miniaturization is giving something called a super paramagnetic limit, and new technologies like pattern magnetic media or perpendicular magnetic media and so on are coming up. So the primary idea will be sort of to reduce the bit size and to have faster magnetic switching, because the faster the bits are switched and the sensors are switched, faster you can write and read the data. So that's the idea. So you need to look for faster technology, and you have to reduce the bit size. So another technology is the magnetic RAM or magnetoresistive RAM. So here, this is a random access memory. This also works on a similar kind of structure, like a tri-layer structure with two magnetic layers separated by a non-magnetic layer. This is either called a spin valve or a tunnel valve. When they are tunnel valve, you actually, spin valve already it is the spin dependent scattering of the charge carrier at the interface of a two magnetic layer and a non-magnetic layer. In the case of tunnel valve, it is an insulating layer. So here you will read the tunneling magnetoresistance. So electrons will tunnel through the barrier. Okay. So, and that also gives rise to, sort of two resistive state and so on. Similar kind of, output you will get. Nevertheless, you actually put them in a crosswire architecture like that. And at each junction, you will put one of those tunnel valves. And these are sort of the word line, and these are the bit line. So you can send some current to write it through the word line, and by sending some other current to the bit line, you can actually read them. So for reading and writing, you have two different crosswire configuration, and they are done by the Oersted field generated by this current. The current will create some Oersted field that will, I write it, and by sending some other smaller amount of current, you can actually align this layer with respect to this layer, and you measure the resistance and you'll be able to read it. So in a similar principle, you can also have the MRAM. And the good thing is that the MRAM, it uses the electron spin to store information, and it can potentially combine the density of a dynamic RAM or a charge-based RAM, and the speed of SRAM, and non-volatility of a flash memory or hard disk. And it also consumes a very small power. So it has several advantages, and it also can resist high radiation and operates in extreme temperature and condition. Only problem is that the miniaturization. When you are actually reducing the MRAM bits, their switching field, the field you require to switch them, become very high. So if the field is very high, then the current also will become very high. And if you are sending very high current, then there will be Joule heating, and there will be a lot of dissipation. So Joule heating is just a waste of energy. So that is actually now, I mean, not now, few years back, that actually stopped the miniaturization of MRAM, and it was like stuck at 64 MB or 128 MB or something like that. But later on, some new technology came called spin orbit effect that actually, sort of avoided or overcome that bottleneck. And right now, even 1 GB or 2 GB MRAMs are available in the market. I'll come to that. And then you have magnetic domain wall-based devices. And many of those I'm now describing, I will describe many of those theories later on. Right now, I'm just giving you information about the devices. So what it is, you have sort of a magnetic wires, which are, designed in such a way that you can trap a domain wall. Let's say you have a device like that. So this is just a magnetic wire. This is the input and this is the output. And let's say there is a domain wall. You can see that here there is a small domain wall where two, head-to-head domains are actually, sort of configured. And here you have no domain wall. In the output, you have no domain wall. So if you consider this as one state, this will be zero state. If you consider this as zero state, this is one state. So now how you, reverse it? If you now rotate a magnetic field, then that will actually, sort of slowly drag this domain wall across this notch. And at some point, it will bring it to here. Okay, so now the domain wall will be pushed here and it will be brought here. So now this will become a zero state, this will be one state. So this can just act as a NOT gate, for example. So just by rotating a magnetic field, you go from 0 to 1 state. So input is 0, output 1, input 1, output 0. And logical mistake is only 10 to the 5 cycles. So, and then another thing based on this, nanowires came up is the magnetic racetrack memory. And this is a 3D architecture, and you can see this kind of nanowires can be designed and can be placed on a substrate, and this has a shape of a racetrack, and that is why they called racetrack memory. And it was discovered by Stuart Parkin in IBM, then at IBM, and now he is in Max Planck Institute. And basically here you can see you can actually create a lot of domain walls here, and each domain can be considered as a data bit. And you can push the domain walls by sending current or magnetic field, or even spin current, like later on I will show you. And you can actually, in a 3D architecture, and here the data density will be huge, because in the planar structure, you can only have this XY plane, but here you also have the Z direction. So you can actually cover the whole XYZ, space to store data here. And here also, you can read and write data in a similar way by sending current or magnetic field, or also by spin current. I'll describe later. So another interesting technology is called the spin torque nano oscillator. Like I was saying, that you can have a microwave, because all these technologies are actually in the microwave frequency of several gigahertz. Your processors and everything are now working in gigahertz. So in order to power those up at those gigahertz frequency with significant power, you can also use magnetic devices. So this is a schematic of this architecture. So here you have again a tri-layer. you have a ferromagnetic layer, a non-magnetic layer, another ferromagnetic layer. So this ferromagnetic layer is called the spin filter, and this is a spin detector, let's say. So if you send a DC current through this ferromagnetic layer, so because it has a spin split band structure, the ferromagnet has spin split band structure, so this current will become spin polarized. And depending on its band structure, the spin polarization will be different. For certain material, it can be very close to 90% or close to 100%. So now the spin polarized current can actually, if this barrier is thin, it can ballistically flow through this barrier and come to this layer, and the magnetization of this layer will now experience a torque because of the spin polarized charges, and that torque is called the spin transfer torque. Okay, and this spin transfer torque can switch or perturb the magnetization of this layer, and when they are switched or perturbed or precessed, they actually emit spin waves, and the spin waves has a frequency of the order of gigahertz. So you can actually get gigahertz frequency radiation out of this. And an individual such oscillator can give only 10 nanowatt of power, output power, which is very small. But the interesting thing is that if you can synchronize them, then the power will actually increase. So if you have an array of such oscillator, and if you synchronize them in phase, that is, if you phase lock them, other words, then the power will grow as n square. So if n is the number of synchronized oscillator, power will grow as n square. So if you have 10 such oscillator, power will be 100 times of that, and 100 times 10 nanowatt will be a microwatt, which will be quite sufficient to power up the computer. And at the same time, you can see that individual oscillators radiation is like that. When they are phase locked, then they become very sharp and very high, tall. So this will now become, so this is phase synchronization of the spin torque nano oscillator is one of the important research in magnetism or spintronics now. So the other thing is, of course, magnonics, like I was saying, which is something that we work on very rigorously these days, which actually work on the principle of spin waves. So what is spin wave? Spin wave is nothing but collective precession of spins or magnetic moments on atom in a magnetic solid. So the spins are actually not moving; they are only precessing around their equilibrium position, but they are connected by Heisenberg exchange. So there is a certain or small phase shift between them, and this phase actually propagate as a wave through the medium. So you actually see a wave moving through the medium, and that wave is called spin wave. So because there is no physical movement of charge, so there is no energy dissipation because of similar to Joule heating or anything like that, and that is why it is very energy efficient, and it can actually be in 2 dimension and 3 dimension. And one can see that if these spin waves can move through a periodically patterned media, something like that. So here you can see in a plate, you have periodically patterned grooves or holes, which are also called nano antidots. So here it can actually gives rise to a band structure like that, similar to electronic band structure. Many of you have seen what is electronic bands and band gaps, like in a semiconductor or metal. Here you can see these magnons of spin waves actually can also create such band structure, band gap, and so on. And they are in gigahertz frequency range, so they are very much useful in all these sort of applications. Okay, so I'll come to that. So magnonics is propagation of spin waves or magnons through periodically modulated magnetic media that open up magnonic band structure and band gap. And this band gap can be in gigahertz to sub-terahertz frequency, which is generally not so available. Okay, and because of spin wave has a very small wavelength as opposed to light wave or other kind of wave. It has for same frequency, gigahertz to sub-terahertz frequency, its wavelength is in the nanometer. So it actually perfectly fits with the nanoscale technology. And that is why you can actually use them for on-chip communication, which is not possible for other kind of microwave sort of device. Okay, so yeah, so how magnonics came up, actually it came up even in 1970s when certain people started to work on propagating spin waves through periodic magnetic media, and then photonic crystals were discovered in late 80s, and then also people started to work on sort of spin waves through periodic magnetic media more vigorously. And in 1996, the first time Gazoued et al. And in 1999, Walsh et al. They worked on the theory and experimental part of this, and they had shown magnon band structure. And then Nikitov et al. In 2001, he coined the name magnonic crystal. And immediately people actually realized the potential of it, and study of research in its fundamental and applications came up. And in recent times, people have actually developed a magnon-based transistor, full magnon-based transistor, logic devices, holographic memory. We actually developed magnetic vortex-based transistor. And there are many interesting physics problems like Skarmion dynamics driven by magnon, non-reciprocal sort of propagation, which can also give rise to drift current, magnon drift current, directional coupler, voltage control logic, and so on. I mean, a lot of new things are coming up, even quantum information processing, where you have hybrid properties like cavity, magnon, polariton, and so on. Okay, so it actually opened up a huge branch of magnonics, which is actually developing very fast. And you can see it has so many branches starting from magnon, Bose-Einstein condensation, magnonic crystal. You have propagating spin waves through various material. You have spin transfer torque, spin orbit torque, you have spin Hall effect, Rashba effect, antiferromagnetic resonance, topological insulator, 2D material, wild semi-metals, various topological objects like solitons, domain walls, vortex fermions, spin pumping, dephasing, and all are converging towards devices, many devices like spinner filters, waveguides, interferometer, transistor, logic, etc. So it actually opened up a completely new area of magnetism and physics. And here is a multifunctional magnonics, like I was showing. So it has an input with an excitation medium. You have a propagation medium where spin wave will propagate, and you have an output when you have a detection. So input can be given either by optical or spin current, thermal, electrical, spin transfer torque. Control can be done by various medium or various external properties like strain, spin pumping, spin Hall effect, and so on. And it can also be detected optically, electrically, and so on. And I'll show you that how the kind of technique that we have developed can be used for excitation, control, and detection of this. And it can also be used for spin transport, for spintronics also. So I was saying there is something called magnonic crystal. It's a periodic magnetic medium. So this is an artificial crystal, like you have normal crystal. There is a lattice, you have a basis, and so on. Similarly, you can artificially create crystal or a metamaterial, you can say. Okay, and these are based on the spin wave quasi-particle. And here you can see the microwave frequency and various bands of microwave, and they can all be covered by spin waves. So you can cover almost all the band of microwave by spin wave. And these are like schematic of 1D, 2D, and 3D magnonic crystals. And these are some of the 2D magnonic crystal. We are also developing 3D magnonic crystals in recent times. I'll not go into that. So some of the 2D periodically patterned magnetic media which can act as magnetic crystal. Of course, magnetism, it has, like I said, or nanomagnetism has applications in bio, medical, technologies, and so on. And one of them is, of course, the targeted drug delivery and hypothermal treatment. And you know that if you have a magnetic field gradient, it will it will apply or exert a force on a magnetic particle, and it is given like m dot del B, However, Fm can be also be written as del chi V times chi times del half B dot H. Okay. So the good thing is that this magnetic force is proportional to the gradient of the magnetic static energy density, and it acts along the direction of the steepest ascent of energy density. So what you can do, you can now attach a drug to a nanomagnet and inject it to the patient's body. And externally, by using a magnetic field, you can move it to a specific area, location of the patient's body by a magnetic field. And this way you can limit the release of the drug. You will not release the drug everywhere. And then you slowly, withdraw it and you release the drug to the specific location of the body. And that will avoid adverse side effects to the healthy cells. For example, if you have healthy cells all over the body, only certain part of the body is affected, you can release the drug only there. And hypothermal treatment, as you know, that a cancer cell has more susceptible at more than 42 degrees centigrade than normal cells. So what you can do, you can increase the temperature locally at that part. So again, a dose of magnetic nanoparticle can be injected into a region of malignant tissue by an alternating magnetic, and then an alternating magnetic field is applied. And this nanoparticle has a certain resonance frequency. If the frequency of the external alternating magnetic field matches with that, they will resonate. And when they resonate, the nanoparticle will absorb energy from the external field, AC field, and it will increase the temperature locally of that part. Okay, and with sufficiently strong field and optimum frequency, it will actually create the sufficient heat of more than 42 degrees centigrade locally, but the surrounding tissues will not be affected. Only the infected cells, you can actually take them to there and locally you heat and you can do this hypothermal treatment. So now I go back to the textbook. We start from here. I know sort of 12th standard, the foundation of electromagnetism. You all know that all these gentlemen, they sort of starting from Oersted to Ampere, Gauss, Faraday, Lorentz, they actually made the foundation of electromagnetism. We know that how the Oersted field was defined. So when you have current flowing through a conductor, it actually gives a magnetic field using this principle. And this gentleman, Maxwell, he actually made a correction is Ampere's law and collected all this and gave us the famous Maxwell's equation, which we all know how to solve them and we do it all the time. And also there is called something called Lorentz force, which was proposed by Heaviside in 1889 and also validated by Lorentz. So Heaviside's name are actually missing from the history, unfortunately, and so on. Okay, so that actually laid the foundation of electromagnetism. And then the magnetic materials, they were also discovered way back in let's say, diamagnetism was discovered in 1778. It was shown in bismuth and antimony. It was repelled by magnetic. We know that a diamagnetic material has a negative susceptibility like that, and its chi is actually constant with T. And then 1905, actually Langevin proposed the theory of diamagnetism and paramagnetism. And for paramagnetism, of course, diamagnetism is nothing but the electrons orbital are changed by an external magnetic field, giving rise to a change in the magnetic signal. Whereas in paramagnetism, you need a permanent atomic magnetic moment due to the unpaired electrons at the outermost shell, but it has no net magnetization at zero magnetic field because they are not interacting by any internal field. So as soon as you reduce the field, the magnetism will be zero. Okay, so you have a M versus H like that, and it is something like that. Okay, paramagnetic, it becomes completely disordered, and this is chi versus T. But then something was discovered in called ferromagnetism by Wise in 1906, and here you can see that it can actually retain some magnetization. So when it retains some magnetization, it will have some hysteresis, and the energy retained can be found out from the area under this curve. and so on. So the holy grail of ferromagnet is that there is some internal field which Weiss described as a molecular field, and he gave an expression like that, H plus gamma m. So this gamma m is the molecular field. So Weiss was correct. He was wise, but he didn't give any explanation for the source of the molecular field. Okay. So that was there. And of course, there was antiferromagnetism and ferrimagnetism and so on, other things, other magnetic materials were there. The point is that this question remained that what is the nature of this internal field and so on. And Heisenberg explained that this molecular field comes from the quantum mechanical exchange interaction. So we just come to there. So if you take the Hitler-London model for hydrogen molecule, we have two electrons with a function psi R1S1 and psi R2S2, and it has a distance of RAB. Okay, and then the overall wave function from Pauli's exclusion principle says that this wave function must be antisymmetric. So either the space part, so it has a space part and a spin part. So either the space part will be, here the space part is symmetric, but the spin part is antisymmetric, or the space part itself is antisymmetric, spin part is symmetric. And by doing a lot of calculation, you actually come to this kind of expression where you have a symmetric wave function like that, which has s equals to 0, overall spin equals to 0, also known as the spin singlet, and energy Es is given by a square k12 plus j12, where j12 is the exchange integral and k12 is a coulomb, whereas you have also antisymmetric, which is given like that, and it has you can see it has s equals to 1, 3 different spin configuration. So you have +1 0 -1 spin singlet triplet state, and the energy of this triplet state is given by b square k12 minus j12, and this j12 is this exchange integral which is given by such expression. So phi a star r1, phi b star r2, h12 phi a r2, phi b r1, d tau 1, d tau 2. So for a parallel alignment of spins, this j12 must be positive. Okay, so when the interatomic spacing RAB is large compared to the radii of the orbital, so and this condition is fulfilled only for D and F band wave function for some certain iron group elements, iron, cobalt, nickel, and so on, and some rare earth metal like gadolinium and so on. And that is why they are actually ferromagnets. Okay, so for a 2 atom, you can write this as -2jij si dot sj, and for a crystal, you have n number of atoms, so you can write this so Je can be taken out of this. It can be considered as isotropic. Most of the time Je actually anisotropic. So if you consider this isotropic, so it comes out, and then you have si dot sj summation over ij. Okay, so you can have a different kind of exchange. Of course, we are talking about the direct exchange so far, where the electron wave functions are actually overlapping directly, but there can also be various indirect exchange, like super exchange, for example. Here, like manganese 3 plus and 4, they are actually, the wave functions do not directly overlap, but they actually overlap through an oxygen ion. So here you can see the oxygen is sitting here. You can also have the RKKY interaction, where the exchange actually occurs through the itinerant or conduction electron. They are mediated by conduction electrons. And there are various other anisotropic exchange. I will talk about it, which is known as the interfacial or bulk Zylowsinski-Moria interaction. So this exchange is actually isotropic, because si dot sj, anywhere you go, it remains isotropic. And from here you can see that because a negative sign is here and J is positive for a ferromagnet, so the energy will be minimum when this term will be maximum. So Si dot Sj will be maximum. So this is, sort of, you can consider it as S square cos theta. So cos theta will be 1 when theta is 0. So that means when the spins are parallel, So then this term will be maximum, overall energy will be minimum. And so the parallel spin configuration gives rise to the minimum energy state of exchange energy. Okay, so just remember, we can remember this, and we'll see that how that compete with a dipolar interaction, because a dipolar interaction, the energy is minimum when the spins are anti-parallel. Okay, and we'll see how they give rise to domains. So there is a criterion called Stoner criterion. So here it says that of course we know that the electron bands actually spontaneously split into up and down spin. So you can see here up and down spins, and this happens with the relative gain in the exchange interaction. That is, the interaction of electrons via Pauli exclusion principle is larger than the loss in the kinetic energy. So energy in the up state can be written as epsilon k minus I times n up minus n down over n, where this term is called the spin polarization. This term is the exchange energy, and E down is epsilon k plus I n up minus n down over n. Okay, so the magnetic moment is given by, of course, the difference in the density of states in this kind of configuration. And the Stoner criterion for existence of ferromagnetism in a metal is I times this d, EF should be greater than 1. Okay, so this DEF actually can be given by 1 over W, which is sort of the the width of the band, and this is given by 1 over T square root of Z. Z is of course the atomic number of the nuclear charge, and T is the interatomic hopping parameter. Okay, so in order for this to happen, for this Stoner criteria to fulfill, sort of iron transition metal series, the hopping parameter is reduced. So this T is less, so D becomes large, and Z is, of course, it varies from element to element. So the hopping parameter is something which is important, or the sort of bandwidth. So then this condition can be fulfilled. So iron transition metal series, the hopping parameter is reduced, and because of that, this criterion is fulfilled, and you can get ferromagnetism in there. So now I come to the magnetic energies. The free energy of a magnetic material, total free energy, can be written as the Zeeman energy plus the interaction, sort of dipolar interaction energy plus the exchange energy and the anisotropy energy. These are the standard you will get everywhere. There can be additional energy terms because of other effects, but this is standard. And you can see in presence of an external magnetic field, the Zeeman energy can be written as minus integral of m dot h dv. Okay, so h is the external field, m is the magnetization. And the self energy due to the magnetostatic field interaction among the magnetic dipoles in a magnetized body. So this is given by minus half m dot h dqr. And the potential energy associated with the stray field can be written as sort of a volume charge term and a surface charge term. So rho v is minus del dot m, rho sigma is equals to m dot m. And this is magnetic charge we are talking about. So the energy can be now be written like an expression like that. Exchange energy in sort of continuum approximation, we have already shown that for the discrete spin model, it is si dot sj. But for a continuum approximation, we are considering the gradient of magnetic field instead of just discrete spin. So here we can write it at a integral over v del m square dq bar, where a is given by 2je square over a is the exchange stiffness constant. Okay, and magnetic anisotropy, which is coming from the spin orbit coupling in a crystal field interaction of the electrons. Okay, it is given by like that. For a cubic system, it is like that, and hexagonal system like that. And why magnetic domains actually appear? The theory was developed in 1906 by Pierre Ernest Wise. It is the competition between the dipolar and exchange interaction. So as I was saying that the exchange interaction is trying to make the spins parallel, the dipolar interaction is trying to make it anti-parallel. But the good thing is, so they will compete. Good thing is that the exchange is a short range interaction, whereas the dipolar interaction is a long range interaction. So they will, have a settlement that exchange interaction will win in the short range, dipole interaction win in the long range. So you will have the domains, and within the domain spins are parallel, but the domains themselves are not parallel. They are making angle or anti-parallel to each other. So this is a multi-domain kind of state where bright and dark will, indicate the two oppositely aligned magnetic direction. So what happens, why domains are formed, it can be very nicely shown from here. So here, this is a single domain state, and you can see the spins are in this row have no nearest neighbor on this side. Okay, so the exchange interaction will be, very high here. Exchange energy will be very high here. Here they are compensated, right? They are interacting with each other. So in order to minimize the energy, it actually will, the field will come out here, what we call as field lines, and try to minimize by going to this tail. So from this head to tail. So this is the field lines. Actually, these field lines for a single domain magnet actually are, sort of wasting energy because the fields are coming out of the material. There's a loss of energy. But if the field can, sort of complete its, field line within the material, they can have a closure kind of flux within the material, then it will be, energy will be minimized. So if you have a situation like that, it is slightly better, but still it will come like that. It will come out a little bit, not this much, but little bit. Okay. But if you have a domain, closure domain like that, now you can see the flux is, completed within this material. So this is the, equilibrium, much stable equilibrium state, because here the energy is not being lost. Okay. And this is why the domains are formed. This is called a Landau domain. This is called a vortex domain. Here you can see the spins are forming spiral, and the center, the spins are coming either up or down. So this is called a vortex core, and these are called the, vortex spirals. This is a ring vortex where spins are forming a vortex like that. It can also form onion-like state. And here these are some quasi-single domain state. Here you can see this form a C state, S-like configuration, flower state, leaf state, and so on. Of course, here you can see the domains are, side by side, but you can understand that if two anti-parallel spins are lying side by side, it will cause huge exchange energy. So this is not possible. So actually, this is not, this domain wall that we are drawing here like that is not like that. It actually has a span or a width. And if you actually zoom it here, you will see like that. So here you can see the domains, this red and blue are the up and down domains, and they actually rotate gradually. Okay, and this part is called the domain wall. Okay, and that is minimizing the exchange energy, loss of exchange energy. This is called a nil wall because it is in the plane of the rotation is in the plane of the film, and for a block wall, it actually goes out of the plane and come like that. So this is called a block wall. You can have cross tie wall, you can have a 360-degree wall, and so on. And this domain wall width can be written like that, where J is the exchange energy, S is spin, K is the anisotropy energy, A is the lattice constant, and so on. And let's say for iron, it is 0.5 times to the -5 centimeters. So now I come to some fundamental time scales of magnetization dynamics or spin dynamics. So you can see that it spans from a femtosecond to microsecond. And this fundamental exchange interaction, like I was saying, it is in a 1 femtosecond time scale. Spin transfer torque or spin orbit coupling forms in this, fall in this time scale about hundreds of femtosecond or something. Laser-induced ultrafast demagnetization, something that I will try to explain a little bit, will form in this range. And then you know about the precession, Larmor precession. So this precession fall in this time scale. Magnetic vortex, I just showed you. The core switching fall in this kind of picosecond time scale. Spin waves which form in this time scale, and domain wall motion fall in microsecond time scale. So the reversal, how the reversal occurs. So we know that magnetic hysteresis loop, but we don't understand from here that how the reversal is actually occurring. What is the microstate, magnetic microstate forming during the reversal? Okay, so it's a very complex non-equilibrium and non-linear, non-local phenomenon. The rotation of magnetization occurs in the mesoscopic length scale, and the micromagnetic free energy has to be minimized, and a phenomenological expression for the coercive field can be written like that. So the coercive field is actually alpha k, which is a structure dependent constant. K1 is the anisotropy constant, mu 0 ms. Ms is the saturation magnetization, and then there are two more terms minus d effective ms. D effective is related to the magnetostatic interaction, and delta H is a correction term. Of course, there is always an offset or other things. So that is there. So you can see that the coercive field is not just the anisotropy constant. There are many things associated with it. So one should, from the coercive field, in order to find out the anisotropy constant, you have to actually model it correctly. Now you can see this rotation, magnetization rotation occurs by various, modes. Here, this is called the coherent rotation. Here you can see all the spins are rotating in unison together. But there can be incoherent rotation, which are like completely incoherent, no pattern. This is for a sphere, this is for a disk. But there can also be slightly incoherent rotation, but they have some pattern. So this is called a curling mode. So they are curling around this cylinder. This is the buckling mode. You can see they actually buckle, and this is called a fanning mode. There can also be other modes like corkscrew mode and so on. So some people actually spend their whole life in order to understand this kind of magnetization reversal, modes in different kinds of materials. And this coherent radius actually depends upon the exchange length and the shape of the ferromagnet. For a sphere, it is like 0.5 time exchange length, and exchange length, which is given by square root of a over mu 0 ms square, which is of the order of about 4 to 6 nanometers for different materials. So from here, you can see the coherent radius is of the order of 20 to 30 nanometers. Okay, so only there it will be coherent rotation. If you have much bigger, sample, it will be incoherent. Then I come to the precession, how magnetization precession occurs, and that is given by a famous Landau-Lipschitz-Gilbert equation. So this Landau-Lipschitz-Gilbert equation to magnetism is similar to, you can say, this is a master equation, like you have a Schrodinger equation in, quantum mechanics or Lagrangian, Hamiltonian, other thing in classical mechanics. So this is a master equation, and this was developed by Lev Landau and Evgeny Lipschitz in 1935. Okay, so the equation, first I will show you the equation is something like that. And then this equation not actually was derived, but you can actually get it from, by combining various, terms. So the equation is like this. It's dm dt is minus gamma m cross h effective, which is the precessional torque. So h effective is the effective magnetic field, m is the magnetization. The cross product will of course give you a torque. Gamma is something called a gyromagnetic ratio, which is nothing but the Landau G factor times Bohr magneton over the reduced Planck's constant. And then alpha is the sort of dimensionless damping parameter, and m cross dm dt is something called a damping torque. So and sort of schematically you can see this is the dm dt, this is m, this is h. So this is a tangential force which is allow it to precess in this cone. But if there is no damping, it will just continuously precess for all the time. But of course there is a damping because the spins are connected to the lattice, so there is a spin lattice interaction and various other interactions. So the energy will finally dissipate and it will align to this direction. So there will be a damping term which is along this direction, and it's given by m cross dm dt. Okay, so now you can see the commutation of spin observable S with Hamiltonian operator can be written like this: I h cut d dt. S is given by sh. Well, this is the commutation bracket. Now this interaction of S with the magnetic field induction vector B is given like that: H is minus g mu b over h cut S dot B is the Hamiltonian. Okay. And the commutation rule for the spin operators are like that: SI Sj is I h cut epsilon jk sk. So now if you use this, you can actually, from here you can get that this commutation can be written as Ig mu b s cross b, okay, by doing some mathematics. So now you can actually write this as d dt of s as g mu b over h cut s cross b for a single spin, okay. But in a macro spin, you will have a large number of spin, and you can write this as g mu b over h cut, average of s. So from here you can write dm dt is minus g mu v over h cut m cross h, or minus gamma m cross h, where gamma is actually given by g mu v over h cut. Okay, so and then a relaxation term was required, and Landau and Lipschitz gave a relaxation term like that, Rm h effective. They have a slightly different term, which was m cross h, whereas Lipschitz later on give, sorry, Gilbert, T. Gilbert actually gave rise to this term, alpha over n is m cross dm dt. So actually this can also be written in terms of m cross h. So this is called the Gilbert's, damping. So Landau Lipschitz also had their own damping term, but Gilbert damping is much more accepted now, and they are interconvertible. Okay, so this is the master equation for magnetization precessional dynamics. So like I showed you before, this is the term, and the internal field or the effective field can be written as H external plus the internal field like demagnetizing field, anisotropy field, and exchange field. And the equation can be linearized and under small angle approximation, and can be solved to have the eigen frequency. So this is eigen frequency is given by omega, which can be expressed like that. So b plus nx minus nz times js plus b plus ny minus nz times js, where nx, ny, nz are called the demagnetization tensor. So for different material, this tensor is different, and you can actually calculate sort of the eigen frequency for different kind of material. At the same time, here's the uniform eigenmode in the system. But there are other kind of modes in the system, the spin wave modes, which are not uniform, and they can be written simply as mRT as m0r times a plane wave, which is for I k dot r minus omega t. This is the space part, and this is the propagating part. Okay, so here you can see the spins here are all precessing around their magnetization, around their equilibrium at a different phase, and as a result, the phase is propagating like a wave. And you can assign a wave vector and a wavelength and a wave vector to this spin wave. This is the actually this was a movie, it doesn't work these days. So I mean, you can have a three-dimensional motion of sort of a spin wave. And the spin waves have different origin. You can have dipolar interaction and you can have exchange interaction. As I said, exchange interaction is as isotropic. Heisenberg exchange is isotropic. And in the textbook, you can read in Kittel or something that omega is actually given by 1 minus cos kr. And in the small wave vector limit, you can actually have k square. So you have something like a parabolic band structure. Whereas the dipolar interaction is not actually isotropic. This exchange interaction, in any direction, it will be the same. Dipolar interaction will depend on the direction of the magnetic field and the magnetization. And here you can actually see that the frequency versus k times d, wave vector times thickness, have three different kind of configuration. Here, this is called a surface wave, which propagates along the surface of the material. And here, the magnetic field and the wave vector are perpendicular to each other and in the plane of the sample. And this is kind of the dispersion. And this dotted line is the FMR frequency, or the ferromagnetic resonance, k equals to 0. This is the dispersion for surface wave, and these two are the dispersion of volume wave. So volume wave will have its dispersion propagate through the volume of the material. And you have this forward volume geometry, and this is the forward volume and this is the backward volume geometry. In the backward volume geometry, you have a negative dispersion. Of course, at a higher wave vector, everything will be exchanged. So it will now, everything will actually merge like that. So here you can see things are actually merging to the exchange interaction. But in the low wave vector regime, they are very different. Okay. And these are their dispersion. You don't have to, remember anything from here now. So what happens to this spin diagram? So now I will tell you that, sort of how the different spin dynamics actually occur in a ferromagnet. So if you take a laser, and I was saying there is something called laser-induced ultrafast demagnetization. These occur in femtosecond time scale. And femtosecond is about 10 to the power minus 15 seconds, which is extremely fast, whereas the precession occurs in picosecond and damping occur in sort of nanosecond. So a very broad range of time is covered here, which is not very easy to measure. So it can be measured only by optical technique, by using a laser. Okay. So what happens that if you have a material, magnetic material, and you apply a magnetic field, and the material is saturated, and you apply a femtosecond laser to it. So there will be an interaction of the material with the laser beam. So initially there will be a coherent interaction between the photons and charge and spin. Okay, and this is can be described by this Dirac equation. But soon this coherent interaction will end and it will enter into an incoherent interaction regime. And there actually the magnitude of magnetization changes. It actually reduces. It can even go to 0. And it can alter the equilibrium position. So that is called the demagnetization. That is, you are demagnetizing the sample even in presence of magnetic field just by the interaction with the femtosecond laser. And there is a lot of debate on the mechanism of demagnetization, and I will describe this in detail in the next lecture. And after that, there will be remagnetization. The magnetization will start to recover. It will not be demagnetized forever. So as soon as you take out the laser beam, laser pulse, so femtosecond laser is a pulse. So you have a train of pulses. So between two pulses, you have no laser pulse. So during that region, so using one pulse, you can excite it, and then when it is reduced to 0, or the laser power is withdrawn, then you can actually see it to recover. So it recovers, so it's called the remagnetization. And then you can see there is a 3 temperature, equilibrium. I mean, you have an interaction between 3 temperature baths. So you have electron temperature, spin temperature, and lattice. And even the specific and other parameters are different. This can be described by something called a 3 temperature model. And when the electron and spin energy are transferred to the lattice, then the lattice will start to gain energy and the physical heating of the system will start to take place. And there an effective field is launched inside the lattice, and you will see that that will kick a precessional motion in the system, and you'll start to see precession and damping in the system. Okay, so the next thing, why my screen is hello.
Yes, sir.
Yeah, my screen is stuck some. Okay, fine. Okay, so experimental techniques. So as I said that you can measure these by various techniques. So the different experimental techniques in the time domain, it is called the time resolved magneto-optical Kerr effect. As I say, it will be an optical technique. And here the excitation can be by optical, electrical, or other means like spin torque. The detection is of course optical, and it has a spatial and time resolution. So you can both resolve it spatially, you can have a spatial map, and of course you have a time resolution. You'll also have a frequency domain measurement. Of course, in the frequency domain, you cannot measure this femtosecond demagnetization or other thing. You can only measure the resonance, the precession, the magnetization, precessional dynamics, and damping. So here, the excitation is by electrical or spin torque excitation, and then detection is also electrical, and it has a frequency resolution. And there is another optical technique, but this is a wave vector resolve technique, where you actually try to measure the frequency versus wave vector or energy versus wave vector EK kind of diagram. This can be measured by Brillouin light scattering spectroscopy. So here excitation is by thermal energy or electrical energy or optical energy or even spin torque energy. And detection here is also optical, but this has no time resolution. Recently, time resolution has been introduced here, but generally, conventionally, it has no time resolution. And it has wave vector and spatial resolution. So what is magneto-optical card effect? I think many of you know, but I'll just go through it. It is simple. It is whether card effect or Faraday effect. It is like if you have a linearly polarized light that is reflected for card effect, and if it is transmitted, it's called Faraday effect, reflected from a magnetic medium. So it will become an elliptically polarized light. And this card rotation and ellipticity will give you a measure of the magnetization of the sun. So let's say you have a linearly polarized light, and after that it becomes elliptically polarized light. So here this is the card rotation theta k, and this is the ellipticity. So this either by theta k or epsilon k, and depending on this elliptical profile, theta k or epsilon k will be larger or smaller, but this theta k and epsilon k are related. So it is like theta k plus I epsilon k is k over r for k less than r. So from here you can actually sort of measure the card rotation or ellipticity. Of course, experimentally you can measure it in different configuration. So actually this magneto-optical effect, it actually introduces an orthogonal component k here in the electric field vector of the reflected light, both in plane and out of plane to the reflected light. The in phase component actually contributes to the card rotation, and the out of phase component will contribute to the card ellipticity. And there are three different configurations. There is the longitudinal, transverse, and polar configuration. And here you can see that the magnetization is actually in the plane of the sample and in the plane of the incidence. So this is the plane of incidence. So they are all in plane. Okay. I is the incident and R is the reflected vector, and K is this additional orthogonal component because of the card rotation. For the transverse, it is also plane of the sample, but it is actually the magnetization is perpendicular to the plane of incidence. Whereas in the polar case, the magnetization itself is perpendicular to the sample, but it is in the plane of incidence. Okay. So that's the difference. So in longitudinal and polar case, upon reflection, the linearly polarized light, that is P or S polarized light, will be converted to elliptically polarized light. Transverse smoke is slightly different. It occurs only for P polarized light. And here the reflected light remains linearly polarized, but its amplitude changes as the magnetization reverses from plus M to minus M. Okay, so it is generally not used for measurement of, this magneto-optical card effect or anything like that. So either the longitudinal or polar effects are used. So how the time resolved magneto-optical card effect works? It is actually a pump probe technique. So you take a femtosecond laser. So here, let's say you have this is the schematic of a femtosecond laser. And I'm not going into the details of laser today, but it is pumped by a solid state laser. And there is something called a phenomena called mode locking, which actually creates the, ultra short pulse. In this case, it is about 80 femtosecond pulse width. And we have another system. This is an amplifier. Here the pulse width is even smaller. It is 35 femtosecond. So you take such a pulse, and then you can split it into two parts. One part is actually called the pump. It has a very strong energy, a high power. It is sent through a second harmonic generator. So the red beam is becoming blue here because the frequency is doubled. The wavelength becomes half. So 800 will become 400. And this will be used to excite the sample. And through different optics, it will be sent to the sample for the excitation. And the probe beam will be, remain the fundamental red beam. And after various paths, it will be sent through an optical delay line So this is nothing but a 180-degree reflector, which is called a retro reflector, which is sitting on a motorized delay stage. So by moving that by computer, you can continuously change the optical path, relative optical path between the pump and the probe. And then finally they are recombined, and then they are sent together to the sample. Together mean in space. In time they can be changed. Their phase or time can be changed by varying the optical path. So here the pump and probe are actually, because this is a microscope, so there is a microscope objective, and they are together, they are focused on the sample to a sub-micron laser spot. So here you have not only a time resolution but a spatial resolution as well. Okay, and the back reflected beam will be, both pump and probe will be back reflected and be collected by the same lens, and the pump will be not be analyzed because we want to see what happens in the system after excitation by the pump, and that we measure by detecting the probe. Probe is for detection, pump is only for excitation. So we will reject the pump beam after that. So we'll filter it out, and only the probe beam will be sent to the detector. And we'll see what is the change in polarization in the probe beam, and that will be proportional to the magnetization of the sample. So by measuring the polarization change in the probe beam, we'll actually measure how the sample magnetization has changed with time and in space. Okay. So this is a non-invasive technique, and by using this, we can measure, different kinds of material from thin film, nanostructures, multi-layers, and so on, and different kinds of properties. And we use a very, important detection technique by using an optical bridge detector, which can measure extremely small car rotation. So I was saying that car rotation, but this is not in several degree. In most of the cases, the car rotation is of the order of several micro degree. Especially in the dynamic regime, it is very small, extremely small. So this system is able to measure that. And this is a non-collinear system. The principle is same, but here we have more power in the pump and probe, and also the time scale is also small. It's only 35 femtosecond, so you can measure it with higher time resolution. So these are the laboratory different view. So this is the full view. If you enter the lab, you'll see that the lasers are here. All the detection, the lock-in amp. These are measured by lock-in amplification, control units, the delay stage control unit, and sort of different other control units are here. The sample is also sitting on a piezoelectric scanning stage, and it is also controlled. So a lot of things are there, and this is the laser. This is the pumping sort of pump laser. This is the femtosecond laser, the second harmonic generator, and these are various optics, delay line, and so on. Okay, we can also have a viewing system and so on. This is another view here, and if you go to here, the detection part is somewhere here. So almost all the parts are being aligned by my students all the time. So many of these, if you're interested, you can note down these references and you can read quite a bit from here. Okay, like I said, the excitation can be done by a magnetic field pulse. So here one can have a transmission line. This is a microwave coplanar strip line. Okay, and this is a kind of a Austin type, photoconductive switch made on gallium arsenide by gold, and they are connected, and here a power supply is connected here. So if you excite this photoconductive switch by a femtosecond laser, it will generate ultra fast sort of carrier, and they will recombine, and so they will create a very fast current in the system. This current will propagate through these transmission lines like that, and they will create very fast magnetic field. So if you place your sample in this magnetic field, they will experience a very fast magnetic field. They will experience precessional dynamics in the system, which can be measured by sort of optically by the technique like I was showing here. Okay, so this is electrical excitation. You can also have an all optical excitation where the excitation is done directly by the laser. So here, sort of ferromagnetic material, band structure, the electrons near the Fermi levels will be brought above the Fermi level, and it will create a population of hot electrons. And then this equilibrium, after non-coherent interaction will give rise to the femtosecond demagnetization and so on. So this all optical excitation is the only way you can actually measure the ultra-fast demagnetization in addition to the precession and damping. Okay. So detection scheme, like I was showing, it can have two different detection scheme. One is by simple photodiode, another is by using quadrant photodiode. In a polar configuration, the beam is coming like that, and back reflected beam will go to here, and a polarized beam splitter, a Glam-Thompson like beam splitter, will split it into two orthogonal components. You can measure it by two photodiodes, and if you take the difference between the two, you get the car rotation, and if you take the sum, you will get the total reflectivity. Okay, and if you actually have a half wave plate here, sorry, a quarter wave plate here, you can rotate the polarization, and you can actually have convert it from car rotation to ellipticity. And this is the longitudinal detection. Here you can see it is coming at an angle. Here it is normal incidence, so it is an oblique incidence. And here you can actually measure by using this quadrant detector the longitudinal and transverse components as well. So this is a non-collinear geometry. Here we are using a big femtosecond amplifier system, and here you have also vary the wavelength by using an optical parametric amplifier. This is a non-linear effect, and this is the sort of the bench, optical bench, and this is the system. I'll not get into that. So this is the one of the typical time resolved car rotation data and initial processing I was trying to show you. So this is sort of car rotation as a function of time. So here you can see that here you have a flat region. This is called a negative delay. Negative delay means the probe has arrived the system or the sample, but the pump has not arrived yet because there is a time delay between the two. So there is no excitation taking place so far. So this is sort of, you can say, the saturation magnetization of the system. And here the pump arrives, and this is called a zero delay when the pump and probe are arriving at the same time. Okay, there is no time delay between them, it's called zero delay. And here the rapid decrease in the magnetization takes place because of the demagnetization. So within few tens of femtosecond to hundreds of femtosecond, it demagnetizes to a very small value. And here the demagnetization is complete, and after that it starts to recover. This is called the fast recovery or fast remagnetization. This is in several femtoseconds. And then there is a slow remagnetization or slow recovery, but that is associated with an oscillation. So this beautiful oscillation of magnetization is the precession. Spins are precessing, and it is actually giving an oscillation in the damped oscillation because there is a damping also. So if you take this data and sort of remove the demagnetization part, or sort of analyze it separately, and then you can take the precessional part and you subtract a background, by exponential background, you will get a beautiful damped oscillation here. And if you do a fast Fourier transform of that time domain, you can convert it to the frequency domain. So we'll get this frequency spectrum of the precession. Okay, so this is the power versus frequency. So you get this peak, which corresponds to the precessional frequency. In many cases, we see after the demagnetization, there is a rapid oscillation, which is actually a terahertz generation. And here this terahertz has a field frequency of the order of 2 to 3 terahertz. So this is called a Brillouin light scattering. It is an inelastic light scattering technique. Here, an incident photon will be scattered from, let's say, a magnon or a phonon, and the scattered photon will have a different energy and momentum. Okay, And depending on whether a magnon is created or annihilated, you will have a Stokes or an anti-Stokes lines, just like Raman scattering, inelastic scattering. But here the difference is that the Stokes and anti-Stokes lines are very close to the Rayleigh line or the elastic line. And the Rayleigh line is huge. It is about a billion or trillion times more than this. So then it becomes extremely difficult because the Rayleigh line will, sort of block the whole, measurement. And for that, you need a very, very, sort of ultra, high, resolution spectrometer, which is called a tandem Fabry-Perot interferometer. So this is sort of schematic. So here you have a sample. Here you have the laser, which will be incident on the sample. And this is a scattered beam. You will not take the reflected beam. Reflected beam will be in this direction. The scattered beam will be collected by this lens. But even in the scattered beam, you will have a lot of Rayleigh line beam. And then after certain optics, it will be taken to this tandem Fabry-Perot interferometer, which has two Fabry-Perot interferometer, which are at certain angle, and they together working in tandem. And there's a multi-pass actually. There are single pass, but there are 3 + 3, 6 pass Fabry-Perot interferometer. And by adjusting the angle and the difference, you can actually reject all the modes, but keep only the mode you try to measure. And the bandwidth is 1 to 500 gigahertz. Resolution is about 0.3 gigahertz. This is this sort of Brillo light scattering with a tandem and Fabry-Perot interferometer in our lab, and this is a microfocus or Brillo light scattering microscope. So here in the Brillo light scattering microscope or the microfocused one, you can actually excite the spin waves like this. So for example, this is a antenna. This is a microwave antenna by which you can excite it, and you can image by doing a scan. You can actually image the propagating spin wave, which is extremely difficult to do actually. Okay, and one can actually see how the spin waves are propagating, and this is a Y junction, how the spin waves are splitting. Either you are sending through this or this. Okay, so I think I'm nearly out of time. This is nearly 4:23. So I'll very quickly talk about the ferromagnetic resonance, and then I will stop today. And rest of the things I'll discuss in the next lecture. So ferromagnetic resonance actually describes the resonant absorption of electromagnetic radiation, or generally microwave radiation, in a magnetic material containing strongly exchange coupled electrons. So if omega internal is equals to omega RF. Omega RF is the external RF frequency. Omega internal is internal resonance frequency. Then there will be a resonance. So in a conventional FMR, you have a cavity, you have a resonant cavity, and the sample is kept within the cavity. And cavity has its own resonant frequency. Okay, let's say resonant frequency is 10 gigahertz. So it can only measure the 10 gigahertz frequency. It cannot measure any other frequency. But a resonant frequency of a material can be varied by an external magnetic field. Because as you have seen before, that omega depends on the field. So by varying the field, you can match the resonant frequency of the material with the cavity resonant frequency, and there you can, so you do a sort of magnetic field scan, and you will be able to measure that. But you can see that for a various magnetic system, you can have many eigenmode. Okay, so these greens are actually the eigenmode of the system, and you can only measure one of those modes. And then you have to again vary the field, and you have to measure these modes, so which is very cumbersome. And that is why a new FMR called the broadband ferromagnetic resonance was discovered or invented. And here you have, instead of a resonant cavity like that with a very high Q factor, you have a non-resonant cavity with a flat and broad Q factor. So here this can measure with sufficient efficiency all the eigenmodes of the system. And that is there called the broadband FMR. Here one use actually something called a vector network analyzer, which has a microwave source or a signal generator and a receiver and analyzer. Okay, So this is called a vector network analyzer, which is very expensive equipment, but very beautiful equipment. And here you can measure either return loss or other things, but the best thing is to measure the scattering parameters. Okay, so this is the schematic of those. So this is the incident beam, this is the reflected beam, transmitted beam, and also in the other port, if you can have two ports basically. In the other port you can have reflected and transmitted beam. This is the device under test, or DUT. So this is called S21 parameter. This is S11. This is S22, and this is S12. And the scattering parameters are defined like B1 over A1 when A2 equals to 0. S21 is B2 over A1, A2 equals to 0, and so on. In the reflection geometry that I will show you in our measurement, we are measuring primarily this. So A2 equals to 0. So this part is actually shorted. So we can short this part of the transmission line. So everything will be reflected. Okay. So like that. So transmission line, here you can see that this is the ground plane. This is the central plane of the transmission line. So here this end is shorted. So when we launch this is the microwave probe. When you launch the microwave here, it will come here and be reflected and come back and will be collected by the same probe. So this is a probe station. It's a home-built probe station. We built everything by buying the different components. This is the, this is a coaxial cable, and this is the probe, and this tip of the probe is shown here. This is called a ground signal ground probe. It goes up to 40 gigahertz. And this is a schematic of the experimental setup. And you can have waveguides of different measurement configuration. Like I was saying, this is the shorted line where we measure primarily the, in the reflection geometry, and the sample is sitting here. This is the sample. So these are the gold lines. The microwave will come here, will be propagated and be reflected back and will be collected here. But in the path, it will face the sample twice. So sample will absorb the microwave frequency twice, and this absorption will be shown up in the measured, signal in the receiver. And this is the transmission geometry. Here it will be transmitted from this end to this end. Okay. This is for propagating spin wave. Here, instead of the sample sitting like that, the sample, this sort of pink regions are here. So here you will have a shorted, waveguide like that, but that will only excite the sample. This will not measure the, detect the spin waves. So now the spin wave will propagate along this direction, and you will have another, sort of antenna like that, which will now inductively couple this excitation or the spin wave excitation, and it will measure in this part. So here you will measure purely the propagating spin wave. In this case, you are not measuring the propagating spin wave. We are only measuring the resonant spectrum. And here, before the measurement, we do a lot of calibration. These are like open short load calibrations. These are done very regularly to reduce different stray or spurious signal in the sample. And this is a typical FMR spectrum. So you can see as a function of different magnetic field, the resonant mode frequency is varying continuously like that. And if you collect all of them and have a surface plot like that, you will see that how the resonant, the white line is actually the experimental spectra, which are lined up or stacked up to give rise to a beautiful, so intensity is in the Z direction, the Z plane. Okay. Within the plane, you have frequency versus magnetic field. And this is the complex, because a complex signal. So you have a real part and the imaginary part. Imaginary part will give you a derivative signal of that. And as I said, the FMR frequency is given like that. So you can do a fit of that and you can find out various material parameters in this sample. So I will stop here because I ran out of time. So in the next class, I will start from this spin orbit effects and so on. Okay. So if you have any question or anything, you can ask.
Thank you, sir. Any questions per participant? You can ask question to sir. Right.
Hello, sir. If I means replace the light signal
Yeah,
through spintronic waves, then can I think this magnetic circuits in parallel with the photonic integrated circuit?
yeah. Basically, what you are saying that in a photonic circuit, you are doing all the communication by photons.
Yes.
You can actually replace everything by magnon. And the
So,
good thing is that magnons are have less dissipation, so it will be more energy efficient. And magnon has a smaller wavelength. Photonic circuits are larger because photon wavelength is of the order of micron, several micrometer. But the magnon has a wavelength of nanometer. So you can actually reduce the circuits to smaller circuits actually.
okay. Then, sir, what will be the typical length of a magnon coupler? Means,
Magnon coupler will be of the order of 10 to 100 nanometer. It can be
oh,
hundreds of nanometer maximum. Because now people are working a lot on the short wavelength magnonics where they are trying to excite very short wavelength magnon, sub 100 nanometer.
oh,
So if the
700.
wavelength is of the order of 50 nanometers, the circuit can be of the order of 100, 200 nanometer maximum.
Okay, but I think it could run in parallel with photonics, but it cannot be replaced. I mean, it cannot replace photonics because there we achieve the speed of communication or maybe broadband communication. So how can Sprintonics will deal with that?
Look, in in a if you are considering replacing the CPU, for example, by photonic magnonic circuit, okay.
Okay.
So there we do not need any photonic component actually, because already we have the magnetic density storage and memory are made of magnetic material. And
Yes.
you only need to communicate between them and process the signal by certain other, right now you are doing it by electronic circuits, okay, charge-based circuit. If you
And people,
replace that by spin waves, then there is no problem. You can store the information and you can transfer the information from one part to another part by spin waves. So here, photonic, we do not compete with photonics. Photonic has other kind of application like on-chip communication for other kind of systems, optical communication and so on. So and because it has a different, and another difficulty with photonics is that photonics or the photon do not have any such easily available anisotropy. Of course, there are anisotropic material, but in magnons or in magnetism, anisotropy is readily available. And as a result, you can very easily move the magnons in any direction. You can turn a corner, you can split the signal very easily. So all these things are done much more easily and also in a smaller space and more efficient, energy efficient. So does that answer your question? Or?
Sure, sir. Actually, I was just running these things parallel in parallel with the photonic crystal concept that you showed the magnetic
Mm-hmm.
crystal. So the
Right.
concepts are same, but here things are quite parallel, sir. I observed, and it's quite new thing for me to see it. I'm
Mm-hmm.
working on photonic integrated circuit. So
Okay, nice. So you can do actually we also borrow a lot of ideas from photonic because photonic crystals came earlier.
yeah, yeah, I saw these things are very much similar actually.
Hmm.
1D photonic that we call photonic crystal, here we call magnetic
Right.
like crystal.
Hmm.
Yes, yes.
Right.
Okay, it was really nice talk, sir. Thank you.
Thank you.
Thank you, sir. Any other participants have any questions? Please ask. If you don't have any question, then we will close the session. Devanjan.
Thank you, sir, for your nice presentation.
Thank you.
Sir, I have a question regarding this spintronic effects around. Just I want to understand. I understood. I want to understand the thing.
Your voice is not clear actually. Please check your mic.
Am I audible?
Yeah, you are audible, but not voice is clear.
There's a noise, but I try to understand. Yeah, say.
So thing is that I want to understand a little bit more about this thing. So about the periodicity in this kind of magnetism, the spin orbit effect you have told. So, so I think what is the, what will be the best possible choice for us to increase the spin orbit effects by, should we use the quasi-periodicity or simple periodic crystal for this kind of?
Yeah. There are two things, of course. I have not come to the spin orbit effect yet. Spin orbit effect, I will, discuss in the next lecture. But in terms of the periodicity, like you said, you are right. I mean, of course, the band structures and the band gaps will be due to the scattering of these spin waves at this sort of periodic, you can say periodic defects, you can say. Okay. So now, depending on the periodicity, the band structure and the band gap will be very different. So if you have a quasi-periodicity, you will not have this, standard band structure. So for example, if you have a square lattice, you have this, gamma X, Y, kind of Brillouin zone and all this. So which will not be, so you will have the full band. In the case of quasi-periodic thing, you can probably have some mini band, but you will not have the complete band. Okay. So, mapping the full, Brillouin zone. So, but of course, we are also studying quasi-periodic crystals and magnonic quasi-crystals and so on, because they can give rise to various kinds of flat bands and localized spin wave modes, and those are also important for various kinds of applications. Okay. So, I mean, they have different kinds of applications, and all of them have to be combined in a way. A single kind of crystal will not deliver your the purpose.
Actually, I have seen some, recent past that quasi-periodicity is, now there is a boom on the research on this topic. So that time I didn't understand why the people are going for the quasi-periodicity, although that offers that doesn't offer the advantages like periodic material. So what kind of application that is actually particularly used to, particularly derive the people to develop this kind of quasi-periodic crystal?
Yeah, like I said that, quasi-periodicity will give you a much more complicated or much more rich band structure. So it can actually generate new bands, which you are not able to get in a periodic crystal. So if you have new bands, of course, you can, have transition between those bands also, and you can have, short wavelength transition and so on. You can localize your, sort of spin wave. If you have in certain case, you want to stop. Not always you have to propagate. You probably have to stop certain frequency. It's called a stop band. So there you can use that kind of structure. Okay. So there are many other applications, of course. So if you want to couple between different, kind of circuits, you probably need certain, sort of coupling band, and there this kind of crystal can be used. I mean, quasi-periodicity can be used.
So we can make some filters also, sir.
Yeah.
Like you want to some stop band is there, pass band is there.
The goal is to make filters, attenuators, couplers, splitters, and this kind of things, of course.
Thank you, sir. Thank you. Thank you very much.